Experiments 10 and 11 are essentially going to be a repeat of experiments 2 and 3. We're going to try to determine an equilibrium constant, and in this set of experiments, we're going to determine the KSP of lead-2 iodide. Now, a KSP is a specific type of equilibrium constant. It's an equilibrium constant for a specific reaction. Much like a Ka is the equilibrium constant for an acid ionizing in water, Kb is the equilibrium constant for a base ionizing in water, the Kw is the equilibrium constant for the autoionization of water, the KSP is the equilibrium constant for a solid salt dissolving in water. And for the salt lead-2 iodide, the KSP will be the equilibrium constant for the reaction PbI2 solid is in equilibrium with Pb2 plus aqueous plus 2I minus aqueous. If we try to write the equilibrium constant expression for this reaction, it would be the concentration of the lead-2 ions multiplied by the concentration of the iodide ions squared divided by nothing because the reactant is a solid, and this is a characteristic look for a KSP expression. It's the concentration of the ions that are dissolved divided by nothing, and that's where the name comes from, solubility product. It's the product of the solubility of the ions once they've dissolved into a solution. Now, experimentally, there's two ways to determine a KSP to start an experiment to do this. You can either take a large amount of the solid, in this case the lead-2 iodide, then dissolve it in a given amount of water, and if the amount of lead-2 iodide is greater than the solubility, all of the solid won't dissolve. But you'll reach an equilibrium where the solid will dissolve and the dissolving will crystallize at equal rates and an equilibrium will establish. We're going to do a second way. We're going to actually take a solution that has very high concentrations of lead-2 ions and iodide ions, and they will start to crystallize. But there's so many lead-2 ions and iodide ions in the solution, they will not all crystallize. So we'll reach a solution where the dissolving process and the crystallizing process become equal in terms of their rates, and an equilibrium will be established. Now, in order for us to calculate the equilibrium constant, we'll need to be able to measure or determine experimentally the equilibrium molarities of the lead-2 ions and the iodide ions. We'll do this by knowing that one of the two reactants happens to be a colored component. And if this substance here, the iodide ions, are a colored component, we can use spectroscopy and we can actually determine the concentration of the iodide ions in our equilibrium solution if we measure the amount of light they absorbed. So to use this technique to determine the equilibrium concentration of this colored component, we're going to need a relationship between the absorbance of the colored species, the iodide, and its concentration. So that's going to be a calibration line, and that's what we're going to be doing in experiment 10. We're going to be setting up an experiment to determine the calibration line relating the absorbance of the colored species with its concentration. So in part A, we're going to prepare a stock solution, and let's go through the calculations in order to determine the concentration of our colored component, which will be the iodide ions, in the stock solution. In part A, they say you're going to wind up creating a stock solution by mixing 10 milliliters of a 0.030 molar Ki solution that's dissolved actually in potassium nitrate with an extra 20.0 milliliters of 0.20 molar potassium nitrate. So the concentration we're interested here is, what's the concentration of the iodide ions in the solution? There'll be a lot of potassium ions, there'll be a lot of nitrate ions. They're actually just keeping the ion strength high for the solution. It actually helps the precipitation occur, but they're not involved in the chemical reaction whatsoever. So, how do we calculate the concentration of iodide ions in the stock solution, of which we've made 30 milliliters? Well, it's not going to be 0.030, right? Because you have 10 milliliters of 0.03 molar potassium iodide. You're adding 20 milliliters of another solution to it. Its concentration is going to be lower. We have to use the dilution equation. That's MCVC equals MdVd, and we're going to be solving for the molarity of the iodide ions in the diluted solution. That's M sub D. So what are each of the variables here? The MC and the VC are the molarity and the volume of the iodide solution before we mixed anything with it, the concentrated solution. So that would be 0.030 molar Ki, and then the volume would be 10 milliliters. In the denominator is the volume of the diluted solution. It's not 20, right? It's 10 plus 20, or 30. So in this calculation, we're going to determine what the concentration of the potassium iodide is once we've mixed the 10 and 20 milliliters together to make a total volume of 30, and that turns out to be 0.010 molar in potassium iodide. Now, what's the concentration of just the iodide ions? Well, we know that when ionic compounds are dissolved in water, they don't exist in molecular form. There are no Ki molecules floating around in the solution. All ionic compounds dissociate, and they'll dissociate into potassium ions and iodide ions. And because there's one potassium in the formula, the molarity of the potassium ions will be 0.010 times 1. And because there's one iodide in the formula, the concentration of the iodide ions in the stock solution will be 0.010 molar. So this is what we need to determine for part A. Now what we're going to do is we're going to take this stock solution, whose concentration of iodide is 0.010 molar, and we're going to make a series of standard solutions, which means they're known concentrations, by slightly diluting the stock solution so the concentration gets lower and lower, and we're going to have a whole series of about 6 different standard solutions that are created. So part B is the creation of the standard solutions, and there's a little table on the experiment to show you what solutions you're going to make. There's going to be standard solution 0, which is going to be a blank. It's not going to have any iodide in it at all, and that's actually used to calibrate the spectrometer. And then we have solutions 1 to 5, where we're going to be using respectively 8, 6, 4, 2, and 1 milliliters of the stock solution of iodide, this 0.010 molar. And we're going to be mixing it with varying volumes of potassium nitrate, and you may notice that we've got the exact volume so that the total volume of solution is always going to come out to be 10. So what you'll need to do is you'll need to calculate the concentration of the iodide ions in all of these different solutions. And I don't want to deprive you of the joy of doing that yourself, so I'm going to make up a solution. Let's say there was a standard solution 6, of which there is not. And let's say we're mixing 5 milliliters of the stock solution of iodide with 5 milliliters of potassium nitrate. Well, what's going to be the concentration of the iodide ion in this fictitious standard solution number 6? Well, the concentrated solution, the stock solution, is 0.010 molar, and we're going to be using 5 milliliters of that. What are we diluting it to? A total volume of 5 plus 5 is 10. So just like before, we can calculate the molarity of this diluted iodide solution, number 6, by going its original molarity, 0.010, multiplied by its volume, 5, divided by the total volume, 10, because that's how you calculate the molarity of a diluted solution. So the stock solution, 0.010 molar. The volume of the stock solution we're using in standard solution number 6 is 5.00, and the total volume is 5 plus 5 is 10.00, and this comes out 0.0050 molar iodide. So notice it's lower than the concentration of the stock solution. It would have to be. We're mixing water with it. So you need to calculate the concentrations of all the different solutions here so that when we measure their absorbances in a spectrometer, you can then actually plot concentration versus absorbance. Now, in the solution that we've created, we're going to have a bunch of iodide ions in them. Each of these solutions, you're going to know the concentration of iodide ions. They might have a slight color to them, but it's actually not very intense. So what we're going to do in this experiment is we're going to convert the iodide ions into diatomic iodine because they show a more characteristic color in a water solution. And the way we're going to use this is we're going to use a nitrite ion, and the nitrite ion is going to actually oxidize the iodide ions up into iodine. The nitrite gets reduced. The nitrogen in the nitrite ion has an oxidation state of +3, and it's going to get reduced into nitrogen monoxide with an oxidation state of +2. That's a reduction. That's going to cause the iodide ions, which have an oxidation state of -1, to be oxidized up to their elemental state with an oxidation state of 0. And the significance of this is those iodine molecules now will have a more characteristic color. It'll be a yellow color. And so that's what we're going to be measuring. We're going to be measuring the absorbance of the yellow color of the iodine that's created. And now we'll be able to get a relationship between the absorbance of the solution and whatever the concentration of the iodide was that we originally put in here. So by placing each of the standard solutions into the spectrometer, we're going to be able to make a calibration line. And that calibration line will have a slope and it'll have an intercept. And that's what we're going to be trying to determine here in experiment 10. In this particular example, if you read the data that's given on the graph there, it says A minus 456.0, which really does not mean A minus 456. This is just saying the absorbance of our solution at a wavelength of 456 equals mx plus b. M in this case, the slope, 215. X is whatever we're plotting on the x-axis. That's the concentration of the iodide ions. And then we have a slight intercept of 0.028. Theoretically, it would come out to be 0, but experimentally, sometimes it doesn't. So this is the equation you should read off of the calibration line you're going to create in experiment 10. And essentially, it means the absorbance of the colored species will equal a slope, 215. In this case, the units are molarity to the -1, multiplied by whatever the concentration of the colored species is, which is the iodide ions, plus our intercept of 0.028. Then in part C, at the end of this experiment, you're going to prepare several different equilibrium solutions. And these solutions you're going to prepare are going to have high concentrations of lead ions or lead-2 ions and iodide ions in them. And the concentrations will be so high that a good number of the lead-2 ions and the iodide ions will precipitate out. And when they precipitate out, the solution will eventually reach equilibrium, and we're going to leave those until experiment 11 to make sure they're at equilibrium. And then what we're going to do is we're going to try to determine the equilibrium constant for each of those different solutions. So there are 5 possible solutions we're going to prepare here. We could theoretically make all 5, and then in our next experiment, we'll determine what the equilibrium constant is for each of those 5 different solutions. Equilibrium constants are constants, and so that means we should be able to get the same equilibrium constant out of all 5 of those. Now, as a preview from what's going to happen in experiment 11, I've got a post-lab question where you're going to be asked to find the KSP from given data like we have here. And so let's go through a similar example to that. Let's say we're going to make a standard solution, and this is not one of the standard solutions you're making, but let's say you're going to make one where the concentration of the lead-2 ions are 0.0050 molar, and the concentration of the iodide ions are 0.0050 molar. So all these ions that are in the solution have such a high concentration, they all can't stay dissolved, and so some of them are going to start to precipitate out. And if some of them precipitate out, then we're going to wind up creating a solid of lead-2 iodide at the bottom, and there'll be a lesser amount of lead-2 ions and iodide ions in the solution, and we're going to wind up setting up an equilibrium. We're going to let this sit in a chemistry locker drawer for a couple days to make sure the equilibrium is established. Now, when we get these solutions for experiment 11, what we want to do is we want to take out only the solution part, so we're going to filter out all the solid. And so if all the solid gets filtered out, we're going to have a solution that contains the exact number of lead ions and iodide ions that were in equilibrium with that solid just a moment ago before we filtered it out. If we're going to try to calculate the KSP for the salt, we need to know what are the concentrations of the lead-2 ions and the iodide ions. And the one we're going to figure out is the concentration of the iodide ions, because we're going to add a nitrite ion to this. The nitrite ion is going to oxidize all the iodides into iodine, and it's going to turn the solution yellow. And then we're now going to read the absorbance of this solution in our spectrometer. So if we put the solution into the spectrometer at a wavelength of 456, which is the same wavelength we used in experiment 10, we'll get a reading, and whatever that reading is, that's the absorbance, and that's going to be related to the concentration of the iodide ions from the equation that we generated from experiment 10. So if we have this relationship, the absorbance of an iodine solution equals 215 molarity to the -1 multiplied by the iodide concentration plus 0.028, we can just plug in the absorbance into this equation and solve for the iodide concentration. We would have to subtract 0.028 from both sides of the equation, and then we would divide by 215 molar to the -1. And when we do that division, the molar to the -1, which is in the denominator, flips to the top, and the units come out molarity, and I get 0.00100 molar iodide. So what we've just figured out is the concentration of the iodide ions in that equilibrium solution. This is the equilibrium concentration of the iodide ions. So now we have enough data to calculate the KSP. And we're going to do that using an ice table. So let's write the reaction for the dissolving of solid lead-2 iodide in water. The equilibrium constant for this reaction will be the KSP. Now, what were the initial molarities? The initial molarities were what we originally put into the test tube. It was 0.0050 molar of lead-2 ions and 0.0050 molar of iodide ions. Because we have such high amounts of the lead-2 ions and iodide ions, the reverse reaction is spontaneous because we didn't have any precipitate to start, but after the reaction reached equilibrium, there was a bunch of solids sitting at the bottom. So we know the reactant was formed. So we're going to react away X of the lead-2 ions, and we're going to react away 2X of the iodide ions. So these are going to be the two equilibrium molarities. The KSP for this reaction is going to equal the concentration of lead-2 ions to the first power multiplied by the concentration of iodide ions to the second power. So these two values are 0.0050 minus X and 0.0050 minus 2X, with that quantity being squared. For us to be able to figure out what the KSP is, we have to know X. And the sneaky way we're going to Columbo what X is in this particular problem is that the spectrometer has told us what the equilibrium concentration of iodide was. This is so similar to what we did in experiments 2 and 3. Maybe now that we've had several weeks since we've done that, this makes a lot more sense what's happening. So now that we know that concentration, you can set 0.0050 minus 2X equal to 0.00100, and we can solve for X. By subtracting 0.0050 from both sides of this equation, we get negative 2X equals negative 0.0050, dividing by negative 2, and we determine that X is 0.0050. So now that we know that, we can determine what the equilibrium molarity of the lead-2 ions are. They're just going to be 0.0050 minus 0.0025, and that turns out to be 0.0025 molar. So in our KSP expression, the concentration of the lead-2 ions are 0.0050, and the concentration of the iodide ions, as we determined spectrophotometrically, was 0.00100. So if we multiply the lead ion concentration by the iodide ion concentration squared, and now the answer will be rounded to 2 significant figures because the lead concentration was only 2 significant figures, we get a KSP of 2.5 times 10 to the minus 9th.